Okay, we're going to do the Honors Physics CAPM practice number 5. This one's about a rocket. So I'll do this algebraically. It doesn't specify here. You could do it either way. I'm just doing it algebraically here, so it means I'm going to start with the diagram. So draw a really good diagram. There's my rocket. VI is 0, so I don't draw a vector. And at the end of the interval, I'm looking at when the engine shuts off. It's moving upward at some VF, which I do not know. It's moving upward, or it has an upward acceleration of 4 meters per second squared. So that means I'm taking positive as up if I call that positive 4 meters per second squared. And it was upward. The delta x is 2,000 meters. And the delta t is unknown. Okay, so we could solve these. When I ask you for two things, you could solve either one first and use it in the other one. It doesn't really matter. I'll just solve them in the order asked. So we're looking for the delta t, and we know the delta x, the vi, and the a, which means I want the relationship that does not have a vf in it. So delta x is vi delta t plus 1/2 a delta t squared. I'm going to go ahead and use the fact that that's 0 to simplify. 0 is an exception to no numbers till the end. It makes life a lot easier and can fundamentally change the algebra. So we want to take advantage of that. Solving for delta t. So I'm going to multiply the 2 up and divide the a under. And then take the square root. Now, I know that I want the positive root here. When I take a square root, there's always a plus and a minus possibility. I know that I want the positive one. So, yeah, you do have to consider both, and sometimes you do want both. But this is not one of those times. So, if I plug these numbers in, I get 31.6 seconds. Okay, now how fast is it moving at that moment? I could use VF is VI plus A delta T. Now that I know the delta T, if I didn't know that, I would have chosen a different model. So I'll just show you that one, just for fun. So I would have chosen the one without the delta T in it, because I didn't know that at the time. And I want to take the square root of both sides. Be careful with the algebra. This is not, the square root of this right side is not VI plus square root of 2A delta x. You know, in this case, the VI is 0, so you wouldn't have gotten a wrong answer from it, but if the VI was not 0, you definitely would have. You can't do the square root like that. So I'll take the square root of both sides. And then I will get about 126.5 meters per second. Make sure you check the units there. They do indeed work on both of these, but make sure you can verify that, and you are verifying that to see that you haven't made any algebra mistakes. So that's how fast it's moving at that point. Now, this is the part where it gets tricky. After that happens, that's where I'm going to start my problem for the next one. So my rocket is moving at with an initial velocity of 126.5 meters per second at the moment where the engine shuts off. It does not immediately start moving downward, right? It still has a velocity upward, so it's going to start slowing down, but it will go up and then come down, and then we're looking for the velocity right like at the moment that it hits the ground. If you include the hitting the ground part, then the acceleration won't be constant over the whole interval. We can't use our CAPM models. Also, if we went from the launch all the way to hitting the ground, the acceleration changed in the middle, so it wasn't constant. We can't use our CAPM models. You always want to be able to use those models. So there's the ground, and the VF is going to be faster. So I'm going to draw that vector longer. It's now in free fall the whole time. So I'm using up as positive. My acceleration is negative 10 meters per second per second. Go ahead and use 10 if we're just solving problems. If we're in the lab, use 9.8, but 10 makes your numbers nicer. Our delta x can be tricky. The final position is down here. The initial position is up here. So the final position is lower. Our direction of positive is up. The delta x is negative 2,000 meters. If you solve the problem and end up with this like weird sign under a radical and you have a negative and an imaginary answer, like don't just gloss over it, figure out why. And make sure as you're drawing your diagram in the first place that all of your signs are consistent with your direction of positive. Delta t is unknown, and it's going to stay that way because what we want is VF, and we have this other info. So what I'm going to use is VF squared plus 2a delta x. This is a place where your algebra will get you if you don't do it right with the square root. So what we can say about this is the square root of vi squared plus 2a delta x. We can't simplify it any more than that. It's not possible. Also, this is a case where we need to consider the plus and the minus. It's going to be moving down, so we want the negative square root. We have to choose which one we want. Okay, we can plug those numbers in, and it's about 236.6 meters per second, negative direction. All right, there we go.